Welcome to lecture 30 and the last lecture of this course for this semester. This QFT course will not be called complete without having a discussion on renormalization, some discussion. So this is just one lecture which just gives you the overview of the renormalization procedure. We have not done any computation over here, only categorization of various stuff, Lagrangians and the notion of renormalizability or otherwise. So before we start doing that, we have to talk about why we care for renormalizing, and that is because there are divergences in the quantum field theory computation. So QFT is a framework in which we given a model Lagrangian, we compute transition amplitudes for various processes. For example, let's just say consider QED with massless fermion. Massless is being important over here. So fermions are massless, and then I'm looking for, say, electron being the fermion and massless. I'm looking for E minus going to E minus gamma process. Okay, so here is the two initial E minus, and this is the two final E minus, again drawn in blue. Photons are drawn in yellow, and this in pink or red is drawn an internal fermion. Okay, so this is matrix element using the Feynman rules one can write, but what one can notice that there will be certain propagators over here. For example, for this photon in the over here, the intermediate photon, there is a propagator factor called P1 minus P3 whole square. Of course, there is a plus I epsilon over there, but this is a momentum dependent piece. And for this red part, for the fermion, there is P4 minus K whole square piece. Again, plus I epsilon is there, and there is no mass term for the fermion because here I'm taking fermion to be massless. So let's look at this red factor over here. What happens to this fermion? So if K is equal to 0, I can always have a situation where the momentum of the emitted photon is practically 0. In that case, P4 minus K square is roughly P4 square, which is 0. Okay, so that means this particular propagator shoots up. Okay, and this is called the soft or the infrared divergence. So if a charged particle radiates a very soft and low energy photon, then the process is divergent. As far as this matrix element computation will show, there is a way to handle this which is beyond the scope of the course, and anyway in one lecture nothing can be done. Okay, a second case is that K is not equal to 0. So I have some momentum for the photon, but that momentum, the 3 momentum, is parallel to the 3 momentum of P4, the outgoing guy. In that case, P4 minus K is going to be proportional to P4 itself, and so square of that is P4 square, which is again 0 because the mass of the final guy is 0. So this is called collinear divergence, where the energy of the photon is not 0, okay, but it's coming out collinear to the outgoing electron. So the amplitude for that, or quality amplitude for that, is also infinity, and this is called the collinear divergence, which also needed to be treated properly. And again, this is beyond the scope of this course. Okay, now consider the factor in yellow, which is for this intermediate photon, and here if my initial and the final state from electrons happen to be collinear, okay, then again, I mean it's parallel, then P1 minus P3 whole square will be either P1 square or P3 square, okay, which is 0 again. So that will give me another infinity, which is also soft, or it could be collinear. Okay, so so we have to okay, so these are the bunch of divergences we'll have at the tree level. Now let's consider one loop diagram. So this is the diagram, and I can write is d4l by 2 pi 4, and then all the diagrams is gamma nu because is here, and you move in the reverse direction of fermion line, then p slash plus l slash, then gamma mu, and then L slash, and coming back, and the trace of that will appear in the numerator. In the denominator, the denominator of the 2 fermion propagator, which is sitting over there. Now, if the L goes to infinity, the dominant factors in the numerator will be, of course, this d4L goes as d3L dl, and the 2 factors of L is there because P is some fixed momenta, so L is going to infinity, so numerator goes as L square, and the denominator goes as L square times L square, which is L to the power 4, So overall it goes as LDL. It means it has a quadratic divergence, and when L goes to infinity, this integral is quadratically divergent, and this is called the ultraviolet divergence. And this comes because the loop momenta can go to the infinity. Okay, so these are the bunch of divergences that will keep on appearing in quantum field theory computations. So this will appear not because the particles are massless, is because their momenta, actually the momenta of these virtual particles, the loop particles running in the loop, can in principle go to infinity. That gives the UV divergences. And for the IR divergences, I necessarily need particles to be massless. Okay, like the fermions has to be massless, otherwise there is no divergence. So at tree level we have soft or the infrared divergences and the collinear divergences, and this can be regulated by introducing small mass to the fermions or the scalar. If I was looking at instead of fermion some scalar, then again the infrared and collinear divergences would have been there, but if you put some mass to them, then these divergences go away. And this is not discussed in this course. While the loop divergence, also not the detailed computation we don't discuss here, but for the loop diagrams do have the soft infrared and the collinear divergence, but we are only interested in the ultraviolet divergence. So what one does is that first, whenever you have a divergent thing, be it on the infrared side or collinear side or the UV side, I cannot do arithmetic with infinities. So first thing is to do is to regulate it. You put a regulator over there so that the diagram becomes finite, the value of the expressions become finite, and when the regulator is removed, it goes to its normal infinity. So it's very important to put the regulator such that the numbers are finite, and at the end of the computation we'll remove the regulator, hoping that all the divergences are cancelling in a systematic manner. Okay, so if x is a quantity which diverges, goes to infinity, then x minus x is actually 0 as x goes to infinity. Okay, so it's important to know that what is the behavior of infinity. Does it grows like x or does it grows like x square? So x square minus x will always go to infinity as x goes to infinity. So we need to identify what kind of divergence it is, and that is done by regularization. There are various ways of doing it: cutoff regularization and dimensional regularization, and there are some other methods there. None of them is being discussed over here. And so idea is that you first regularize them, and then you add a counter term to cancel this UV divergences to get the finite results. This is the procedure of renormalization. We add a counter term. Okay, so let's move on to understand where this UV divergences are coming from. So it basically stems from the point-like interaction vertices in this diagram, in any of the diagrams. That is, in delta t going to 0 limit, that t is the being time, a finite or an infinite momentum is transferred. So we know that force is delta p by delta t. Okay, and if I take the t going to 0 limit, I'll get the exact thing. This is the finite difference expression for that. Okay, there's finite t. So let's look at this diagram. The blue fermion line is the blue line denotes a fermion which emits a lot of photon. So what is happening that between two interaction point, it moves with a constant momentum, and then it changes the momenta at the point of interaction. It has now different momenta, and there is another particle with balancing momenta, and there's another particle, yet another, and so on. Okay, so from left to right the time is going. So if I have to draw the force, okay, and taking delta t equal to 0 limit, then what I will get, there is no force till this interaction point, and there is a delta function impulse. Okay, so if we take delta t going to 0, the force becomes a series of delta function. Okay, so what is having is we are having that before and after this interaction, we are having the inertial frames. Okay, and the state corresponding to inertial frames, and they're just artificially joined at the interaction vortex. That is what your array and A-Dagger operator are doing, if you remember in the chemical conservation. So here the force or the acceleration is an emergent quantity at large length scale and the large time scale. So I cannot talk about time scales that small. What I have to consider is delta t has to be large enough. Okay, so that within that delta t, delta p is some quantity, and no matter where do I take this delta t, on average I have roughly the same delta p. So your force would be a constant under certain constant given condition. Okay, so force will be an emergent quantity that makes sense only at large length and large time scale. So basically, if I remove the point-like particle with a finite size object, then actually there's not going to be any UV divergence. This is the direction in which string theories goes. Or if there is a smallest length scale in your theory, that nothing can be smaller than this, or nothing can happen at a length scale smaller than that. That is what's called doubly spatial relativity. Like standard relativity says nothing can travel faster than speed of light. So there is an upper limit to that. On the other hand, there's a doubly spatial relativity has that no two different points have distances smaller than this number. Okay, so then automatically for two distant things, there will be a finite length scale and everything will be controlled over there. So there will again be no UV divergence in those theory, but they are far beyond this studies over here. This is just I'm giving pointers. String theory and doubly spatial relativity or any other fancy theory with finite length scale is far too beyond this course. Okay. Now, living with the divergences, what do we do? So Green's functions that we have, the endpoint functions, like endpoint correlation functions, that are basically related to physical observables, and they have to be finite because we measure them in the lab. So this has to be finite, but the Lagrangian and its parameters are not observables. So they can be unphysical or infinite. So what happens is that, suppose I'm looking at this 2-point Green's function and one loop correction to this in the scalar theory. So this is a divergent and order lambda. What I do, I add this order lambda piece, which is also infinity and opposite to this, so that it cancels. Okay. So what is this 2-point function? This might be related to the del mu phi, or it may be related to m square phi square. So this might change the wave function, which is a correction to del mu phi, or it might change the mass of the particle infinitely. Okay, if I'm just looking without the regulator, it changes infinitely, but usually we do in the presence of regulator. It changes by some finite but large amount, okay, those quantities, such that the Green's function that I'm computing, okay, or the process and propagator that I'm computing, that remains finite up to one order, after for next first order. Likewise for the 4-point function, or here that relates to scattering. So what I do, that I have at one loop this order lambda square corrections, and now I add a counter term of order lambda square at a very particular chosen energy, such that all the divergences cancel out. So that these three diagrams at one loop plus this order lambda square counter term gives me finite number. So this additional added Lagrangian things, which I have been already saying, these are counter terms, and we need one counter term to cancel divergence in each of the Green's function to give to a given order. Okay, so the same counter term make several or all Green's function finite. It's possible that I added a counter term over here, and that the same counter term appears in this computation and cancels the divergences over there. Doesn't happen over here because this is order lambda square, but there are certain theories, for example QED, where one counter term is sufficient to cancel a wide variety of divergences. Okay, so this can happen, but usually what happens that what is demanded, that for each Green's function I need one counter term to cancel it. And the example we can consider is lambda phi 4 theory. So this has two parameters, mass and the coupling. These two defines the theory uniquely. The position of the pole in the propagator defines the mass. So you remember pole is 1 by p square minus m square. So if I take the inverse of the pole, so 0 of the inverse of the pole is the definition of mass. So wherever p square, whenever this is 0, that value of p square is the mass. Okay, so this is how I define, and this is how I measure the mass experimentally, so to say, looking at the pole in some resonance thing. So using one measurement, I can fix what is the mass. Using second measurement, which is 55.255 cross section at a suitably chosen energy, that is related to lambda square, because this coupling matrix element is proportional to minus I lambda. We have seen in some lectures. The cross section will be proportional to lambda square. So we measure the cross section experimentally and we fix lambda. So once I have measured m and lambda, then with these two physical measurements, okay, these two physical measurements are directly related to two parameters, okay, and then all the endpoint Green's function in this particular theory at tree level are uniquely predictable from this knowledge. So this is called predictability at tree level. At tree level, I just added this is a definition of predictability, that I use couple of some finite number of experiments to fix the finite number of parameters in my theory, and then I will be able to predict in principle countably infinite number of quantities in that theory if it has that many independent quantities. Okay. Loop diagrams for the Green's functions are divergent. That means we need to add counter term, countably infinity of them in principle. That means we lose the predictability, because whenever I'm adding the term, I have to perform another experiment for each Green's function to fix that. That what they must cancel to give me a finite result, but what is that finite result? Okay, so I need to fix that using an experiment. Now for each Green's function, if I have to perform an experiment, then in my theory, where am I predicting? I'm just performing infinite number of experiments to fix the parameters of my theory, but my theory is never going to tell me that, okay, you go and measure this thing and here it is the value you will find. So there is no predictability. Okay, now let's put predictability and renormalizability together. So case 1 is that all endpoint Green's function diverge at suitably higher order in perturbation theory. So it might happen that endpoint Green's function at lower order, like say tree level, nothing is divergent. You make one higher order, things start to become divergent. Okay, so now if there is an endpoint function that will always going to diverge, okay, at suitably higher order in the perturbation theory, that means we need one counter term for all endpoint Green's function. Okay, there may be theory that so let's systematically say that for given n, there exists some n, you given n, choose an n point Green's function, and there exists some higher order correction that will make that infinite. That means for each of this n point Green's function, I need a counter term. That means we need to measure observable corresponding to each of these n point Green's function to fix the parameter. That means I have absolutely no predictability in my theory. Such theories are called non-renormalizable. I cannot renormalize them. Okay, what is the meaning of renormalizability? Would be that there was some parameter I started with, I needed to fix them to make the theory finite and sensible at a certain order. So case 2 is that we have a finite number of endpoint Green's function diverging, but they diverge at all order. Okay, so only few of them will diverge, some finite number of them, and others will not. So there are values of n for which the endpoint Green's function will not be divergent at any order. But for the cases when it is divergent at all the orders. Okay, if that happens, then we need finite number of counter terms to be added up to the given order of interest. So, and then only finite number of observables we need to fix the Lagrangian. We need to measure them to fix the Lagrangian. So all other endpoint Green's function can be predicted using the numbers that we have just fixed, and such a thing is called renormalizable. In case 3 is that only finite number of Feynman diagrams are divergent. It means not only finite number of endpoint Green's function, but even within a given Green function, if you go to sufficiently higher order, they are all finite. So you only have to compute the certain, say 1 loop, 2 loop, and that's all. And beyond certain number of loops, they are all going to be finite anyway. So that certainly is predictable, and but this is called super renormalizable, because if you can compute all those finite number of diagrams that are divergent and you can regulate them, and if you can cancel them, then the entire theory becomes absolutely finite, as against the renormalizable theory, where it always remains renormalizable to a given order, and the moment you go beyond that order, it requires fixing again. But it only requires finite number of physical observables to fix those things. Okay, so but here for the super renormalizable, if you fix to all those divergent diagrams, then you fix the theory to all order for all Green's function. So that's why this is very, very special. So moving on next, sorry for the background noise. We need to quantify and categorize all these divergences. So we have to define quantities that will take care of how divergent is the divergent stuff. So for that, we define what's called the superficial degree of divergence, labeled by D. And in any given diagram, how it goes is that you count the number of momentum in the numerator minus the number of momentum in the denominator. Exactly what we did when we talked about on the first slide, while I was talking about degree divergence. So what we did, we counted total number of L in the numerator, and that turned out to be 4 here and 2 here. So 6 in the numerator and 4 in the denominator. So 6 minus 4 is 2, it's a degree of divergence would be 2. But this is called the superficial degree of divergence. So if d is greater than 0, which was apparently the case in the first slide, it is called polynomial divergence. D equal to 1 is linear, d equal to 2 is quadratic, d equal to 3 is cubic, and so on. D equal to 0 will be what's called logarithmic divergence. Okay, because dx by x, if you integrate, it gives you log, and log of x for x going to infinity is still divergent. Okay, so d equal to d0 doesn't mean it's finite. Only d less than 0 is finite. Okay, good. Now the actual degree of divergence in a given theory might be different from the superficial degree of divergence, and it could be more divergent than what we have computed using the superficial degree formula, or it may be less divergent. Okay, so what happens if you have a symmetry in the theory? Okay, like for gauge field theory, there's a gauge symmetry. This usually lowers the divergence. So whatever superficial degree of divergence says, you actually have less than that divergent. And if you have a diagram where a sub-diagram, smaller subset of the diagram is divergent, in that cases, your superficial degree of divergence may be some finite, but you will see the actual divergence is more than that, because there is a subset sitting inside, sub-diagram sitting inside, which is divergent. So divergent sub-diagram usually increases the divergence, usually leads to a divergence more than the superficial degree of divergence. So let's quickly have a look at this example. How do we say? Example will take QED. L is the number of loops, P is the number of internal electron propagator, and P gamma is number of internal photon propagator. So what is the degree of divergence? So D is, as written on the left side, is a power of momentum in the numerator, that is 4 times the number of loops. Okay, in D dimension it will be D times the number of loops, so in 4 dimension it is 4 times the number of loops, so it's 4L minus, for each fermion propagator I get 1 by the momentum, and for each photon propagator I get 1 by momentum square. Okay, so this is my formula. So if I look at this diagram, okay, so this diagram has no loops, the L equal to 0, it has no internal fermions, it has no internal photons, all of them are external. So this gives me d equal to 0, and since there was no loop, is actually finite. D equal to 0 usually doesn't mean finite, it means logarithmically divergent, but since there is no integral to be computed, so it is finite. Now let's look at the same diagram with one photon exchange. Okay, and you can see that here number of loop is 1, so that gives me 4, then number of fermion is 2 inside that loop, so that gives me -2, and number of photon is 1, so for one photon I need 2 factors, so -2, so that again gives me degree of divergence to be 0, same as here. But here, because there was one loop, it is a logarithmically divergent. Okay, and it remains logarithmically divergent even with all symmetries of the QED. Now let's look at this diagram where 2 photons are external leg and one loop diagram is there. So here for d equal to d will be 4 minus 2, because the 2 fermion legs, and then there is no photon leg inside, so 4 minus 2 is just 2. This should be a quadratically divergent diagram, that what we saw on the first slide. Okay, it should be a quadratically divergent diagram, but in reality it turns out to be d equal to 0, which is a logarithmically divergent, and that is because of gauge symmetry. Each of this external photon leads to certain symmetric transformation that has to be performed, and that leads to this actual degree of divergence being less than the superficial degree of divergence. So this is an example of symmetry. And here there is another diagram which has a sub-diagram which is divergent. So if you look at the D for the total diagram, it has 4 because it is one loop, -2 because the 2 fermions internal, -2 times 2 because there are 2 more photons over here, which has the internal photons. So it's 4 minus 2 minus 4, which is -2, is the superficial degree of divergence, but is actually, we know that is a logarithmically divergent, that because it has a divergent sub-diagram over here. Okay, so this is the example of degree of divergence being more than the superficial degree of divergence. Then I have this diagram with the 2 fermion, 2 gauge boson being exchanged. So here d equal to 4 minus 2 minus 4, which is -2. This is finite. And if I have this kind of case, where 2 photons are there and 2 fermions are there. If I compute the degree of divergence, it is -1. But so it must be finite, but owing to the Qed symmetry, actual degree of divergence is actually -3. So it is even more convergent than what we have over here. And if you have these 4 photons and connected to a fermion box, here if you compute d, it turns out to be 0. So it should be logarithmically divergent, but it is actually finite and its degree of divergence is -4. This is again owing to the Qed symmetry. Okay. Now, having said this about the having looked at the importance of superficial degree of divergence and how seriously to take them, is that we have to be careful about the subdivergences and the symmetries. Okay, what Weinberg said in 1960 is that a general Feynman diagram is convergent if the superficial degree of divergence for the diagram and all of its subdiagram are negative. So this is one way to show that the diagram is necessarily going to be convergent. Okay, failing any criteria, the diagram need not be convergent. Here it doesn't take care of the symmetry when it says that any of the subdiagram also have the negative degrees of superficial degree. It's the superficial degree one is talking about. One can have a superficial degree to be 2, which is divergent, and still it is only logarithmically divergent. Okay, so that is a way to show how the subdiagrams work. So if we cancel, this is another important thing, if we cancel a particular divergence of a diagram by a counter term, then we also cancel the divergence, that particular subdivergence, in all other diagrams where it appears as a subdivergence. So let's say this is the divergent diagram, which is logarithmically divergent, and I added this counter term, okay, and that gave me finite result. That means that this particular guy, whose superficial degree of divergence was -2, but it was logarithmically divergent owing to the subdivergence. So that diagram also gets cancelled by this diagram. The same, just add 2 fermions line to the photons. So this plus this will still be finite. Okay, and here I'm assuming that this is the only divergence in this diagram, which is the true case in this here. But it means that if this is divergent, then this plus this is finite, and that can happen wherever this particular diagram appears. I can add another diagram where this photon loop, fermion loop in the photon is replaced by this photon propagator with a correction. Okay. So if I add all these diagrams systematically, I will have all the finite results. Or at least this part of the divergence is cancelled. There might be some other divergence available in that diagram. So we need to add counter term only for the diagrams with primitive divergence. That is the divergent after removing the subdivergences. So here, if I remove the subdivergence, then this diagram is finite. So this 4 fermion diagram doesn't need a separate counter term. Okay, so that is what it means. So it is important to take care of the subdivergences. Sorry again for the train noise. Now let's talk about the divergence and the graph theory, and with the example of QED. So let NE be the number of external fermion and gamma be the number of external photon, PE the number of internal fermion propagator, P gamma number of internal photon propagator, V is the number of interaction vortex, which is the N3. So that means that NE plus N gamma is equal to N1, the total number of N1 point vortices, and total number of vortices is V plus N1. So for all the graph theoretic formula, it's a VT that will appear. And total number of edges we have in the theory, which is PE plus P gamma plus NE plus N gamma. These are the number of edges. Okay, and so NE plus N gamma is just N1. So that's simplified. Now we know from graph theory that L is equal to number of loops minus number of vertices plus C, and here we are looking at the C equal to 1. Okay, so for E we replace this formula, okay, with plus N1. And for V, we replace this formula with plus N1. The N1 cancels out, and we end up getting L equal to PE plus P gamma minus V plus 1. So this is my one step. Now I have a modified version of handshake lemma over here. So what happens for each vertex, I have 1 photon. So number of photon in the diagram that I'm doing is same as the number of vertices, but that is same as 2 times the propagator. Okay, because the propagator is connected to 2 different vertices. The internal propagators are all connected to two vertices. Okay, so each propagator in a way is getting counted twice. okay, while counting this vortices thing. The total number of, so this is actually the sum of degrees, but when I'm doing the sum of degrees, I'm only doing the sum of photonic degrees. So how many photons are there at every place? But I'm only counting the internal vortices. N1 I'm not counting. So that n gamma on the left and n gamma on the right. If I counted n gamma on the left should have been V plus n gamma is equal to 2 times total number of photon propagator, which is 2 times P gamma plus 2 times n gamma. But n gamma is appearing both sides, one factor will cancel. So it becomes V is equal to 2P plus n gamma. Now similar if I do for fermions, so each vortex has 2 fermions. So 2 times V plus NE would be 2PE plus 2NE, but NE cancels. I get 2V is equal to 2P plus NE. So this is a different way of writing the number of vortices in terms of photon only, and in terms of electrons or the fermions only. So now if I look at the D expression for D, which is 4L minus 2P gamma minus PE, that's the degree of divergence we computed earlier. So here I just put this value of L, and then I suggestively include this 4 factor of V that will come. So 3 I'll put it with the fermions because the minus 3V is coming. So here I'll get 4 minus 3V minus 3PE minus of V minus 2P gamma. So I'll automatically put it, so if you just expand it, you'll get exact expression that you will get if you put L over here. Now suggestively bracketing means that I can use this formula directly. So 3V minus 3PE would be just 3 by 2 NE from here, and V minus 2P gamma is just N gamma. So eventually what I end up getting is D is equal to 4 minus 3 by 2 NE minus N gamma. So what it suggests that if I have large enough NE and N gamma, my D is going to be 0. Okay, and that has very important consequence, which is to say only finite number of n-point Green's functions are divergent. And when you have only finite number of Green's function being divergent, then the theory has it has to fix by only finite number of experiments. So this will be renormalizable. Okay, so this for the QED. So we'll check further. So let's look at all the divergent diagram of QED. So for NE equal to 0 and N gamma equal to 0, the divergence is degree of divergence is 4, and these are all the bubble diagrams. They are not observable, so we don't care for them. Next comes N equal to 0 and N gamma equal to 1, that has degree of divergence equal to 3 using the formula in the previous slide. And this is a diagram like this, where this blob means anything over here which is connected to a photon. And usually photon is connected to a fermion, so you have basically a conserved current, so time ordered product of single conserved current and sandwich between vacuum, that will be 0. It's a conserved current, so its vacuum expectation value will be 0. Okay, now I go for N equal to 0 and gamma equal to 2, that gives me degree of divergence 2. That was also there on the first slide. Okay, so this is a divergent piece, but the gauge invariance's degree of divergence comes down to D equal to 0. That means it's logarithmically divergent, but it's still divergent, it's not finite. And for N equal to 0 and N gamma equal to 3, this thing will be degree of divergence 1, okay, with 3 photons in it. But this is equivalent to having vacuum expectation value of odd number of J mu's, and that is 0, the same as here, by another argument which comes the odd behavior of photons under charge conjugation or parity. So this is another symmetry argument that kills this guy. Okay, this is exactly 0. Then I have N equal to 0 and N gamma equal to 4. That gives me D equal to 0. And this kind of diagram, one diagram I drew in the previous slide, which has a fermion box in between. So it should have D equal to 0, but because of gauge invariance, it has D equal to -4. So this is perfectly divergent diagram, not to worry. Then it comes to N equal to 2 and gamma 0. So that has degree of divergence 1. And this is a diagram. Ideally it should have degree of divergence 1, but because of what's called chiral symmetry, and that is to the left chiral fermion and the right chiral fermion, if you remember from the first 8 to 9 lectures when we talked about fermions. So left chiral and right chiral are completely different species, and they get mixed by the mass term. So if mass is 0, they never talk to each other. And we also talked about the fact that gauge interactions, like for QED interactions, preserve the chirality, which means that photon connects left chiral to the left chiral and right chiral to a right chiral. It never mixes them. So if they are not to be mixed to begin with, they will never get mixed. But So that is to say, this particular diagram, if the mass was 0 to begin with, it will never have mass. So this particular additional symmetry makes some of the contribution proportional to the mass of fermion. So that is the degree of divergence 1 that I am saying is actually not momenta but mass. And hence the rest of the divergent piece is only d equal to 0, which is a logarithmically divergent. So this another symmetry argument reduces this d for this fermion line. And here for n equal to 2 and gamma equal to 0, sorry, this was 1. This should have been 1, and gamma is equal to 1. Okay. And here degree of divergence is 0. Okay, and this is a logarithmically divergent guy. Okay, so if you look at the 3-box diagram, these are the only divergent Green's function. Okay, and at any loop, so I only have to compute these 3. And there are further one can show is that this guy is related to the coupling renormalization. This is related, and this is related to the mass of the fermions. So just these 2 is sufficient to fix everything. Okay, and we don't need to renormalize this guy separately. So if I needed to renormalize this guy separately, that means that I needed to measure the mass of the photon to be something. But mass is photon is massless, and that happens because this renormalization of this divergence of the 2 photon propagator is actually not required. Just renormalizing these 2 is sufficient to take care of that. Okay, that's additional thing when one does the exact computation one finds. So this was the QED in the 4 dimension. Now if I just to see the arguments of renormalizability, I can go for QED in d dimension. And a similar argument will give me the degree of superficial degree of divergence to be d plus d minus 4 by 2 times v, d minus 2 by 2 times n gamma, and d minus 1 by 2 times ne. Okay, so here if d is less than 4, you can see here, if d is less than 4, then the v is the parameter, v is the number of vortex. If I go for higher and higher order, it will keep on reducing the divergence. So for larger v, more divergent, more convergent. So any diagram is more convergent for large number of vertices. That means only finite number of divergent diagrams exist. Hence the theory would become same QED in dimension d less than 4 will become super renormalizable. If I have d greater than 4, then this factor is positive. That means we have d equal to 0 at suitably higher order for any n gamma or any. You choose your favorite any n gamma. Choose your favorite endpoint Green's function. Then I can always go to a sufficiently large order where the large number of vertices appear, and this diagram will be divergent. That means infinite number of divergent Green's function, hence non-renormalizable. Same QED becomes non-renormalizable in dimensions higher than 4. And for d equal to 4, as we can see, this vortex dependence goes away, and we have the formula already studied, and all these things coming from that 4-dimensional study. So we have finite number of divergent Green's function, and hence at all our higher order. So this theory remains renormalizable. The QED remains renormalizable in 4 dimensions. Now it is a bit of a study to do all these things by looking by doing all this computation in various dimensions and all that, and drawing the diagrams and checking whether they are divergent or not. It would have been very, very nice if you had something more simpler than that I'm just looking at the Lagrangian. I can say which are the terms that are making it non-renormalizable, in case they are making it non-renormalizable, or whether the theory is renormalizable at all. And if it is, then we can proceed with computation. And if it is not, then which terms are following the renormalizability. Okay, so it will be nice to just look at the Lagrangian and do that, and that's where we look at. So when I'm looking at Lagrangian, so what it turns out that the coupling constant has a certain dimensionality, and that is the retro renormalizability. We can quickly discuss that part. So my action is ddl in the d dimension, and s is the same dimension as the h bar, which is set to 0 in natural units. So dimension of L is just t, dimension of Lagrangian density. That is because my x has dimension -1 and derivative has dimension 1. Okay. For Dirac theory, if I write, then it is what I get is 2 times psi plus 1 is d. That means the dimension of psi is d minus 1 by 2. This is what we have been using in the previous slide also. Here, this is what I have used for d dimensions. Okay. And for fermion and boson that we computed earlier, we got for fermion in d equal to 4 to be 3 by 2 is exactly from this formula. And likewise, for the scalar and the gauge boson, the corresponding dimensions are d minus 2 by 2. For d equal to 4, its dimensions turns out to be 1. Okay. Now consider a generic interaction which has in a Lagrangian, which is lambda times psi by psi to the power f by 2, phi to the power s, and mu to the power v. Okay, so a given Lagrangian, a given term in the Lagrangian can have any number of fermions, any number of scalars, any number of mu's. Okay, so if that is there, the corresponding coupling, what is the dimension it has? So it will be d is equal to, because the total thing has to be part of the Lagrangian density, it has to have dimension d. D is equal to dimensions of lambda plus f times d by 2, d minus 1 by 2, plus s plus v times d minus 2 by 2. If I just write lambda here and put everything over here, so for larger number of fermions and scalar and vectors in a given order, the lambda has more and more negative mass dimensions. Okay, for d equal to 4, I can just simplify this formula to be 4 minus 3 by 2f plus minus s minus v. Okay, so if you write a term like m square v square, the dimension of m square turns out to be 2. Okay, because it has 2 scalars and no fermions. For g phi psi psi, so there are 2f over here, so here is 2f means so f equal to 2, so 4 minus 3, that is 1, and there's one scalar, so that another minus 1, so here g becomes coupling dimension 0. Lambda phi 4 likewise is dimensionless. G phi to the power 6. Okay, so there is no f, and here 4 minus 6 is minus 2. So this large number of fields will in 4 dimension will make the coupling negative dimension. Okay, so that is one thing. Next we say, what is the dimension of the matrix element that contains f fermions, s scalars, and v gauge boson, which is okay, so and this turns out to be exactly same as this lambda over here, and the argument is as follows, that if this was the term, whether this term actually exists in a Lagrangian or not, one way to write a Green's function which involves these things is to assume that there exists a term like this, and then your Feynman rules will say the matrix element is nothing but I times lambda. So what is the dimension of this? Is the dimension of this hypothetical coupling. So dimension of matrix element with f fermions, s scalar, and v gauge boson is exactly this formula. Okay, so this is the dimension of f plus s plus v point matrix element in a given theory. Now at higher order, this Green's function will have vi copies of a vertex I with lambda I being the coupling and d being a superficial degree of divergence. Assuming that's the case, then what is the mass dimension of this? I can write mass dimension of matrix element would be sum of the mass dimension of all the couplings. Okay, so vi times mass dimension of lambda I, sum over all i's, plus d. D is the superficial degree of divergence, because these things are constant. Okay, they have mass dimension, but they are constant. When I'm saying but that my superficial degree of divergence is d, that means that my matrix element for large momenta grows as momenta power d. So this is the coming from that. Momentum power d is a factor over there, apart from the coupling constant. So when I compute the mass dimensions, the total mass dimension would have this and that. So I can just say d is equal to mass dimension of matrix element, which can be computed from this place, minus vi times lambda I, where the lambda is can be computed from this place. Although this formula looks exactly the same, you have to look at each term in the Lagrangian for that, for each of the lambda i's. Okay, what happens that if lambda i's, all the lambda i's are greater than 0, that means for large enough number of vertices, large enough order, all the diagrams, all the given a matrix element, it can always have go to higher order, you will have d less than 0. Okay, that means only finite number of Feynman diagram for any Green's function will be infinity. So this is the definition of super renormalizability. If lambda i's for all couplings, or at least one coupling, is negative, then what I can do is that I can, for the negative guy, if I put more and more vertices of negative mass dimension, then I can make this guy always grow. Okay, with minus sign here and negative here, so my degree of divergence can keep on going up if lambda is negative and v is increasing. Okay, so with negative mass dimensions will give me non-renormalizable theory. But if lambda i's, all the lambda i's either 0 or positive, then the theory is renormalizable. Okay, so to say it again, if the theory has at least one lambda I less than 0, then the entire theory is non-renormalizable, although a part of the theory might still be useful. Okay, if a theory has no lambda I less than 0 and at least one lambda I mass dimension 0, that is renormalizable and requires counter term to be adjusted to each higher order in computation, because lambda I 0 means that corresponding Feynman diagram will be divergent at each order. Okay, and if a theory has a lambda I greater than 0 for all I, then it is super renormalizable and can be made finite by adjusting finite number of couplings only at finite number of higher order. Okay, so it is important to check the renormalizability and hence the predictability of a theory before investing the time and energy trying to do the higher order correction, because that's very laborious task. Okay, and I again, sorry for the background noise. I want to emphasize that at the end of this lecture that we did not do any loop calculation over here and no divergence. So loop, we might write the loop expression from the diagram using the Feynman rules, but doing a loop calculation means evaluating those integrals. So we have not done that, and no divergence is explicitly studied here, nor their cancellations. We did only implicitly in this lecture, and that's only the UV divergence because we wanted to study and discuss the systematics of Lagrangian, systematics of the renormalization, that this is what we have to take care of when we have to cancel things. When we actually go into canceling things, that calculation is quite dirty and involved, and that renormalization itself can very easily take 5 to 7 lectures to say the least. And if you in fact this course, or the topic of renormalization is so rich that if you want to study with a bunch of examples, then 10-15 lectures would also not be sufficient. So this is my desperate attempt to do some justice to the divergences in QFT, and especially the UV divergences and renormalization, and how one does the systematics of renormalization, only the overall things. Okay, and only graph theoretical thing that I have done over here, that if you have to prove the renormalizability, you can eventually look at the coupling of the terms and mass dimensions of the coupling of the term in a given, whatever given dimension that you are working the theory on it. So with this, I would say this course comes to an end, and we'll see you at the discussions and other incidences, other events. Bye-bye.